G'day folks, welcome back to another of our video tutorials. We're talking about chemical thermodynamics at the moment. In the previous video tutorial we covered some important terminology. So we talked about heat and temperature and sort of distinguished between the two, distinguished between the system and the surroundings. We distinguished between state functions and path functions, and we distinguished between endothermic and exothermic reactions. And we just started to talk about some of the terminology that you might see. We talked about work, internal energy. We didn't really get to the point actually of talking about enthalpy, entropy and free energy, but we'll sort of get to that. We'll certainly start talking about enthalpy in this video today. Okay, we're going to talk about the difference between internal energy and enthalpy. Okay, these are often confused. They're both state functions. They're kind of similar, but they're actually a little bit different. So let's make sure we've got that distinction right in our minds. But first, let's talk about the first law of thermodynamics. And it's based on three really simple ideas that arise from observations. The first is that energy is conserved, and you could probably conceive some sort of experiment to make that judgment yourselves. This is something that was observed very early in modern physics. Quite some time ago, they performed experiments to determine that energy is conserved. Okay, and we can express that in different ways. You cannot create or destroy energy. You can just move it around and so on. And depending whether or not you're talking about chemistry and physics, you'll sort of word that in different ways. The second point is that heat and work can produce equivalent effects, and I think you guys probably have some sort of feeling for the difference between heat and work. So heat, we defined heat in the last video tutorial. So this is the energy transfer between two different systems, or a system and surroundings, perhaps at different temperatures. Whereas work is something like this poor little guy here pulling this very heavy block. He's doing work, he's working hard. Okay, chemicals often have to do work as well, or atoms and elements, as they sort of, destroy certain molecules and make new ones. They're doing work. You might like to think of it that way. And the other cornerstone of the first law of thermodynamics is based on the fact that the only ways that energy can be transferred is through heat or work. Okay, so let's think about this mathematically. If energy is conserved, this means it cannot be created out of nothing or disappear without a trace. Therefore, any change in the internal energy of a system must be the result of work done or heat change in the system. So we're going to call the internal energy U, and therefore delta U is really equal to Q plus W, whether or not there's been any change in Q or any work done on the system. So there you go. There's a mathematical expression for the first law of thermodynamics. Okay, so energy can be converted from one form to another, for example, into heat, or used to do work, but it cannot be created or destroyed. We can also say the energy given out by a system must equal the energy gained by the surroundings. The energy's got to go somewhere, right? So it goes to the surroundings. The energy of the universe is unchanged. And so you might express this in the opposite fashion as well. But mathematically, we can express it like this. And this is true for any isolated system where the change in the energy of the universe must be equal to the change in the internal energy of the system plus the change in the internal energy of the surroundings. And for an isolated system, this is going to be equal to 0. Okay, so we've got this nice little expression now for the first law of thermodynamics, where we have the change in the internal energy is equal to the heat plus the work. And I've got there heat as delta H. We're going to have a look at that. There are different definitions for Q, and sometimes this will be equivalent to something called the enthalpy, which is indicated by an H. But first of all, let's get this right in our minds. If Q is a positive value, we're saying that heat energy is being added to the system, so the internal energy is increasing. If Q is negative, heat is given out from the system to the surroundings. More generally, a positive sign indicates a gain of energy by the system, from its surroundings, and a negative sign indicates a loss of energy from the system to its surroundings. The sign is really important here. Okay, now let's have a think about this scenario, and I'll bring a little bit of physics into this, not too much, because I know some of you get absolutely terrified even just hearing the word physics, but I know some of you love physics, and that's wonderful, but some of you are actually, quite happily not studying physics in any way, shape or form. So this is a really basic kind of description where we can have a look at how the idea of work might tie in to the chemistry of a system. And the picture that you're looking at here is of a frictionless piston. So like the piston that you might have in the engine of your car or something like that. And what you can see here is that we have, we have some sort of cylinder, and the yellow object there, that might be the piston, which can move up and down. And we have a situation where there is gas inside the cylinder, and there's a little black pin which has been put in just to hold that piston in position. And the gas is under pressure. Okay, so it's larger than atmospheric pressure inside that area, those little blue balls. And we can say that the atmospheric pressure, which is sort of, if you like, on the outside of the cylinder, it's pushing down. And you could say that the gas on both sides of that yellow piston is sort of pushing both ways. If you release the pin, we said that the gas was under pressure, so larger than atmospheric pressure. So it pushes back against that yellow piston, and you can see that the yellow piston moves. And we can say that work is done as that piston moves. Let's just break this down to some nice geometry, and we'll have a look at this. We'll bring in a little bit of physics, but we'll bring it back to the chemistry. Okay, so pressure equals the force divided by the area. Okay, and so that's the pressure of that atmospheric gas. Now, in our little scenario here, we saw that the piston moved up. Okay, and so our chemical system, which is the gas inside the cylinder, you can see that it now occupies a larger volume, and you can see that using some simple three-dimensional geometry, we can say that the area is going to be delta H multiplied by A. So the area of that circle, or the cross section of the piston. All right, let's just have a look at how this might be expressed from a physics perspective. We would say that the work done by the system equals the force, and this is the force with respect to that atmospheric pressure that was being, implied, or you can think of it the other way around as being applied by the gas inside the cylinder. And the work that's done is the force multiplied by the distance. Let's express this algebraically. So we said that the force was equal to the pressure times the area, just a rearrangement of that equation that we saw there, multiplied by the distance. Well, the distance is the height that this piston moved up, yep. Well, I put it to you, we can rearrange that. I'm just changing my red to blue there, and because I'm not going to play a trick with the pressure and the area, I'm actually going to rearrange my equation so that I combine the area with delta H, which, as we can see from our three-dimensional geometry, that's the change in volume. In other words, the work equals the pressure times the change in volume. And suddenly, hopefully you guys are thinking, well, pressure, volume, yeah, we kind of talk about that stuff in chemistry, It looked a bit more like your physics when we started, but this is a little bit more like chemistry. So work equals the pressure times the change in volume. That might be something you can work with. Remind you of the ideal gas equation, of course, which, interrelates the product of pressure and volume with nRT. Okay, so let's think about this. So at constant pressure, the work by the surroundings must have been the pressure multiplied by the change in volume. So the work by the system was the equal but opposite in sign to that. And so the change in the internal energy of the system must look something like this. We saw that work could be expressed in terms of pressure and volume. So we've just re-expressed the first law of thermodynamics. We saw previously that delta U was equal to Q plus W. Well, now we'll talk about it in terms of Q minus pressure times the change in volume. Things that we can measure as chemists. So obviously the conditions of measurement are important. Okay, we said that the work done by the system is negative P times delta V. All right, well, let me throw this out there. What if the volume can't change? What if you perform a chemical reaction inside some sort of container where delta V is always 0, so the volume can't change? I don't know, it's a big, sort of sphere of concrete or something like that. So the volume inside that vessel, if you like, is a constant. So delta V would equal 0. If delta V equals 0, then P times delta V also equals 0, and therefore work must equal 0, right? So delta U just equals Q, and we say Q with a little v. This is the heat of the reaction at a constant volume. We can actually do these sorts of experiments. We can measure the change in internal energy of a system in what's called a constant volume bomb calorimeter, and I'll let you guys look that up in your own time. It's not entirely convenient to do chemical reactions in bomb calorimeters. That's a pretty sort of special case in some ways. More often than not, we might be doing a chemical reaction in a beaker like this or some other sort of vessel. So, the volume is open to being, it could change. It might change by a tiny bit. It might change by a lot. I don't know, but it's certainly not a constant volume. But if it was open to the atmosphere like this, well, we could say that the reaction is done under conditions of constant pressure, right? So atmospheric pressure is pretty much constant. It changes a tiny bit as per the hectopascal readings by the weather person on the nightly news. But generally speaking, atmospheric pressure is pretty constant, right? So delta U of the system equals Q minus P delta V. We saw that in one of the previous slides. And this brings us to a new state function. I'm going to define enthalpy. Enthalpy, which is indicated using the symbol H, is defined as this. The enthalpy equals the internal energy plus P times V. And if you like, if a system has to exist in the universe, it kind of has to occupy some volume in the universe, and to occupy that volume in the universe, if you like, it's going to have to push something out of the way so it can exist. And if it pushes the air around it or something, we might say that's the pressure of the air around it, and the volume is that it occupies. So the enthalpy is just in some ways, it's just a slight correction to the internal energy so that it can exist in the universe. And so we might define it like this: delta H, or the change in enthalpy, equals the change in internal energy plus P times the change in volume. Well, this is actually a handy way to think about energy in a more practical sense. So under conditions of constant pressure, we know that, well, if delta U equals Q minus P times delta V, but we say that enthalpy has this an additional term, a plus P delta V, those two terms are going to cancel. You have a minus P delta V and a plus P delta V. So they cancel, and you get delta H equals the heat of the reaction at a constant pressure. Okay? The proviso, of course, is that the volume of the system can change, and that's probably true for 99.9% of reactions. In other words, where I'm going with this, folks, is that enthalpy is kind of a more practical thing that we can measure in a laboratory than changes in internal energy, unless we were using a bomb calorimeter. So that's enthalpy, and we can write under conditions of constant pressure that this expression, that kind of ties it all up, if you like. So the internal energy of the system, or the change in the internal energy of the system, equals the change in enthalpy minus P times delta V. We'll have a look at calorimetry of a system using something called a coffee cup calorimeter in the next video tutorial.